This video is about reaction rates. By the end of this video, you should understand what is meant by the term reaction rate. You should be able to predict the relationship between the rates of appearance or disappearance of reactants and products based on the stoichiometry of a reaction. And you should understand the difference between average rate and instantaneous rate. A reaction rate is the change in the concentration of a reactant or product per unit time. We can express this mathematically by showing the concentration of substance B at time 2 minus the concentration of substance B at time 1, in other words, change in concentration of substance B, over time 2 minus time 1, or change in time. We could abbreviate this as follows. Rate is equal to delta concentration of B over delta T. In other words, change in concentration of B over change in time. For a reaction that goes to completion, we can imagine that the concentration of reactant will decrease over time, and the concentration of product will increase over time. Again, notice this reaction goes to completion, meaning that at the end of the reaction, all of the reactant has been converted to product. We can express reaction rates as the rate of disappearance of reactant or as the rate of appearance of product. Whichever way we choose, rates are always expressed as positive values. From the stoichiometry of a reaction, we can also determine the relationship between rates of appearance and disappearance. Take this example. Here, 1 mole of A is converted to 1 mole of B. Therefore, the rate of disappearance of A is equal to the rate of appearance of B because of the 1-to-1 stoichiometric ratio. On the other hand, should we have a reaction where 2 moles of A is converted to 1 mole of B, the rate of disappearance of A will be twice the rate of appearance of B, since for every 1 B formed, 2 A's have disappeared. Looking at a real reaction, the reaction between 2 moles of NO2 to yield 2 moles of NO and 1 mole of O2, we can see that NO2 will disappear at the same rate that NO appears due to the 2-to-2 mole ratio. NO2 will disappear twice as fast as O2 appears, however, due to the 2-to-1 mole ratio. And finally, NO will appear twice as fast as O2 will disappear due to the 2-to-1 ratio. Looking at these amounts graphically, we see that the concentration of NO2 decreases over time, while the concentration of NO and O2 increase over time. You should also note that NO is increasing at twice the rate that O2 is increasing due to the 2-to-1 ratio. Also notice that this reaction does not go to completion, since not all reactants have been converted to product. Instead, this reaction reaches equilibrium. Now let's take a different reaction and consider the rate data for this reaction over time. Notice that as time progresses and our concentration of reactant decreases, our rate changes. Our rate is not constant throughout the course of the reaction. From this data, what we can take away is that reaction rates tend to decrease as a reaction progresses. Considering this in terms of collision theory, it makes sense since reactant concentrations are decreasing, the number of available reactant molecules to collide is decreasing. Therefore, we have fewer collisions and fewer effective collisions. This means that the rate of reaction will decrease. However, since the rate of the reaction is not constant throughout the entire course of the reaction, the average rate is not a very useful value. Therefore, we have to use something called an instantaneous rate. In order to understand the difference between average rate and instantaneous rate, consider this graph in which the blue line represents the rate of the reaction over time. Notice the rate is decreasing as the reaction progresses. If we took the average rate of this reaction by, say, taking a point early in the reaction where the rate is one thing, and a point later in the reaction where the rate is something else, the slope of this line would represent the average rate. However, as you can see, the average rate is quite different than the actual rate throughout this time period. However, notice that if we choose a smaller and smaller window of time, our average rate gets closer and closer to the actual rate at that moment in the reaction. Therefore, if we make our window of time so small that we're actually looking at the rate at a single instant, we can define this as the instantaneous rate of change. This red line here represents the instantaneous rate of change. In other words, it gives the rate at any moment during the reaction. The value of the rate then is equal to the slope of the tangent to the curve at that point. So in summary, the instantaneous rate is the rate at a particular instant during the reaction. It's equal to the slope of the tangent to the curve at that point in time. Here's one final analogy to help differentiate between instantaneous rate and average rate. Imagine you took a 100-mile road trip. Your average rate, or your speed on this road trip, might be, say, 50 miles per hour. However, if you consider the way a road trip actually goes, you're not going to be traveling at 50 miles an hour exactly throughout the entire 100-mile trip. At the very beginning of your trip, for instance, you definitely won't be at 50 miles per hour quite yet. At some point in your trip, you may be traveling slightly faster than 50 miles per hour. At other points in your trip, you may encounter some traffic or some red lights, which will slow your rate to below 50 miles per hour. So your instantaneous rate would be the reading of the speedometer in the car at any single point in your trip. If you look at the speedometer at that moment, whatever it's reading, be it 75 miles per hour or 25 miles per hour, that's your instantaneous rate. That brings us to the end of this video. Let's review our goals. First, we looked at what is meant by the term reaction rate, or the change in concentration of a reactant or product over time. Then we looked at how to predict the relationship between rates of appearance or disappearance of reactants and products using the stoichiometry of the reaction. And finally, we looked at the difference between average rate and instantaneous rate.